In this video, we're going to learn how to implement an infinite grid, like this one, in OpenGL. Trust me, it's endless. This grid can be very useful for debugging because it allows us to visually understand the orientation of the camera. You can also use it as the view of the world if you're working on any kind of editor, which is similar to tools from Blender to Unity. If you look closely, you can see that there are actually two types of lines here. There are thick lines with a distance of 10 units from each other. Each pair of neighboring horizontal and vertical lines contains a grid of 10 by 10 smaller squares of thinner lines. In addition, there is some kind of a level of detail, or LOD, system at work here, because only the squares close to the camera have an inner grid. The more distant squares have nothing. What's interesting here is that if we switch to wireframe, we can see that this is actually just a simple square of two triangles. So what's the trick? Well, everything is based on calculating the color of each individual pixel based on several parameters, such as the distance from the camera and the distance from where the grid lines are supposed to be. Okay, before we get started, I'd like to say a big thank you to Marco, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. Okay, let's get started. You already know that this system is based on two triangles, so let's start with that. We can render two triangles as usual, using a vertex buffer or a combination of a vertex and index buffers, but in this case I'm actually going to skip those and simply place the four vertices of the square directly inside the vertex shader. As you can see, we have the bottom left, bottom right, top right, and top left. In addition, we have an array of 6 indices which references the four vertices. Okay, so we have the first triangle and the second triangle. The advantage of this approach is that it reduces the setup of the technique so that almost all of it is self-contained within the shaders. This makes it very easy to copy-paste it into different projects. In the main function of the vertex shader, we use the system variable GLVertexID, which is simply a running index of the vertices in order to access the corresponding index from the indices array. We can now use this index to access the vertex from the vertex array. We extend the vertex from vec3 to vec4 and multiply it by the view projection matrix. Notice that there is no world matrix here. The vertex coordinates are considered to be already in the world. The background is set to white, so in the fragment shader we only need to output a black color. Okay, so if the camera is working correctly, you should be able to move it and everything should look correct. However, this allows us to move away until the square is entirely out of view. This can't be avoided even if we scale up the square. So one of the key principles of the technique is to move the square along with the camera, kind of like the way a skybox works. To get this working, we add the world space position of the camera as a uniform variable to the vertex shader, and we offset the x and z coordinates of the vertex by the corresponding components of the camera position. The y component of the grid is always 0. This step can be challenging to test, and the easiest way I found is to position the camera in front of the grid and move left and right. If everything is working correctly, you shouldn't be able to tell that the camera is moving. Don't worry about the size of the square. We will scale it up later on. Next, we're going to output the world space position of the vertex from the vertex shader. For that, we use the original vertex position before the transformation with the view projection matrix. In the fragment shader, we use the world space position as the output color, and we can see that the color is nicely interpolated across the square. So what about those grid lines? Basically, we want to check whether a pixel is directly on top of a grid line, and if that's the case, change its color. Let's try something. we define a uniform variable for the size of the grid cell in world space, and we modulate the z component of the world space position by this variable. As you can see, the variable is a fraction, but the modulo instruction works very similar to the way the standard integer modulo works. We also define two uniform variables for the color of the grid lines. Right now we simply set the output color to be the color of the thick line, and we multiply the alpha channel by the result of the modulo operation. To get this working, we also enable blending and set the blend function to be source alpha and 1 minus source alpha. This means that the final color is calculated by multiplying the output color of the fragment shader by its alpha channel and adding the color in the frame buffer multiplied by 1 minus the same alpha channel. So when the alpha channel is high, the final color is closer to the grid line color, black by default, and when it is low, it is closer to the background, which is white. We can see that the modulo operation kind of interpolates the color, and we can play with the grid cell size and verify that we are indeed getting smaller or larger cells. Okay, but we want to get an actual line and not some sort of interpolation. This means that the alpha value should be high on the grid line, and then it should drastically drop to get the background color. Enter the derivative functions of GLSL. A derivative function calculates the rate of change in the values of all vertex attributes as they are interpolated across the triangle face in screen space. Consider the following block of 2x2 pixels that shows the value of some attribute in every pixel. The derivative of the bottom left pixel on the x-axis is the value of the pixel on the right minus the value of the bottom left corner, so we get 1. The derivative of the same pixel on the y-axis is the value of the pixel on top of it minus its value, and we get 3. Okay, so each pixel has two derivatives on the x and y axis, and these derivatives are calculated for each component of every vertex attribute separately. If we compare the derivatives of the same component on different pixels, we can say that when the derivative is higher, it means that the attribute changes more rapidly compared to the pixels where the derivative is lower. For example, when the derivative is 0, it means that the two neighboring pixels have the same value. In GLSL, we use the functions df dx and df dy to calculate the x and y derivatives, respectively, and notice that f is capital and the rest of the letters are lowercase. Now let's try to divide the result of the modulo operation by the y derivative of the z component of the world space position. The result is that we are now getting white lines, while most of the square is black. Let's try to understand this. The camera is pointing along the z-axis, so the lower pixels have a lower z component in the world space position. The higher pixels are more distant from the camera, so their z component is higher. The y derivative of the z component of the world space position represents the delta in the world space z between neighboring pixels from bottom to top. The modulo operation simply causes the z component to go from 0 to the cell size in loops. This is a floating point modulo, so it's not exactly 0, but I don't want to confuse you too much at this point. When we divide the first pixel in this loop by the y derivative, we get a number which is close to 0, but on the next pixel we get about 1, because the change between pixels is the derivative and we are dividing by the derivative. So we get about 1 for the second pixel, about 2 for the third pixel, and so on. This value is used as the alpha component of the result, and as we have seen, when the alpha is 0, we get the background color, and when it is 1 or more, we get the pixel color from the fragment shader. This explains why we're getting white lines over a black background. We will reverse it later on. This works kind of okay when the camera is pointing along the z-axis, but it starts to break when we turn the camera left and right. If we take a closer look at the pixels, we can see an aliasing problem where the alpha value changes drastically between neighboring pixels, which causes a jump between black and white pixels. This is a numerical issue which I have to admit I don't fully understand, so I'll just say that I think it is caused by the fact that the z-axis of the world is now pointing to the side, whereas the corresponding derivative is still calculated between pixels which are on top of each other along the y-axis of the window. This means that the change in the modulo operation, which also goes to the side, is not guaranteed to be in sync with the y derivative. This makes the alpha value continuously go in and out of sync between neighboring pixels, resulting in the aliasing problem. We can improve the situation a bit by multiplying the derivative by 4 before the division. This causes the alpha value to change more slowly, so we get a few more lines before it becomes like the background. Okay, now let's try the same thing using the x component this time and the corresponding x derivative. So we are getting the vertical lines of the grid, but we are also seeing the aliasing problem. The reason is very similar. The center line is okay because all the pixels have the same x value, and the modular trick works for the column of pixels on the left and right of it. But due to perspective projection, the remaining vertical lines are not really vertical, and we end up with the same result as before. Now here's another problem with the current setup. If we go back to the horizontal lines and change the camera about 90 degrees to the right, we suddenly see that half of the screen is missing. The reason is that at this point the derivative becomes negative, which means that the alpha is also negative. A negative alpha gets clamped to 0, and the background color takes over. In this camera orientation, it's actually better to use the x derivative instead of the y, because here the z-axis of the world goes from left to right. So we need to find a way to stabilize our derivatives so that they are not impacted by the camera orientation. What we can do is to create a 2D vector of the x and y derivatives of the z component and use the length of this vector instead of one of the derivatives. In the cases where the value changes on both x and y axes, this provides a more stable approximation of the rate of change of this value. The next step is to combine the two derivatives of each of the x and z components of the world space position in a pair of 2D vectors. We can now calculate the length of each vector and store it in a new 2D vector called du/dv. This allows us to do the modulo operation on the world space position in one go and take the maximum of the two components of the result after the division by du/dv. The result is this field of dots. Can you tell why we're seeing this instead of the grid lines? I'll write the explanation in the pinned comment below because this video is becoming very long as it is. If you understand this, then you should also understand why we get the grid lines with the white background this time when we subtract the current calculation from 1. The current situation is that we can still see a significant aliasing problem across the grid. The reason is that there are still quite a few pixels with a drastic change of the alpha value. We can fix it by saturating the inner calculation, multiplying it by 2, subtracting 1, and taking the absolute value of the entire thing before the final subtraction from 1. Take a moment to consider the following table that shows an example of the calculations. After this modification, the problem is pushed out into the distance. We will mitigate it later on using a more aggressive usage of alpha to blend between the grid and the background. Okay, we need to start working on the LOD system. But right now the grid is too small, so we add a uniform variable called grid size, which we will use in the vertex shader to scale up the position vector. We set it to 100 by default, which seems to make the grid stretch well into the horizon, But of course you can tune it for your own setup. As you can see, we're getting some major artifacts in the distance. I believe that the formal name of this phenomenon is the Moyer pattern, and if you're interested, you can find more details about it in Wikipedia. The LOD should help us fight this effect, because it will make the grid cells larger as we move into the distance. Let's calculate it. We already have a configuration for the size of the grid cell in world space. Naturally, due to perspective projection, the grid cell becomes smaller as we move away from the camera. At some point, the cell becomes so small that the image is distorted. Let's add a new uniform variable for the minimum number of pixels between cells and set it to 2 by default. We know that the y derivative of the z component represents the change of world space z in screen space. Let's divide this derivative by the size of the grid cell. What does it mean? When the result is roughly 1, it means that on every pixel, we switch between grid cells, which is smaller than the minimum that we have just defined. If it's less than 1, it means that we need more than 1 pixel to switch between grid cells. If it's greater than 1, it's even worse than 1. If we multiply this fraction by the minimum number of pixels between grid cells, we can then check the result against 1 and decide whether to switch the level of detail. Before we continue, we will switch the y derivative, which works okay for this specific case, with the lengths of the du/dv vector, which, as we saw, represents all the derivatives together. To actually calculate the LOD, we will use the base 10 log function. In general, the log function is a popular method for calculating things that gradually fall off, like LODs. In this example, we can see the behavior of the base 10 log compared to other log functions. The base 10 log of 1 is of course 0, because 10 raised to the power of 0 is 1. The base 10 log of 10 is 1, the base 10 log of 100 is 2, and etc. We can calculate the base 10 log of the derivative multiplied by the minimum number of pixels between cells and divided by the size of the grid cell. The result will be negative if the input is less than 1 and greater than or equal to 0 if the input is greater than or equal to 1. Let's define the LOD as the whole part of the result after taking the maximum between 0 and the result of the base 10 log. The fractional part will be used later on for the alpha calculations. We can now calculate the first grid cell size as the product of the configured grid cell size and 10 raised to the power of the LOD. This means that when the cell size reaches the configured minimum number of pixels, the cell size will grow by a factor of 10, and we will continue like that until we reach the minimum again. Remember that the minimum number of pixels always coincides with the result of 1 on the base 10 log. The results actually look better if we add 1 to the results of the log function, so let's do that. We will use the new grid cell size, now based on the dynamic LOD, as the input to the modulo operator instead of the configured cell size. The LOD system should now work correctly, but as you can see, the change in LODs is too drastic. We would like to blend between LODs and make it flow more naturally. We start by calculating 2 more grid cell sizes. We do that by multiplying the current cell size by 10 for the next LOD and then again for the LOD that comes after that. We can now repeat the alpha calculations using the 2 new cell sizes. If the alpha of the highest cell size is greater than 0, we use the color of the thick lines, regardless the LOD. So every now and then we get a thick line, even if we are close to the camera. Otherwise, if the alpha of the cell size in the middle is greater than 1, we use the fractional part of the LOD to mix between the 2 colors. And if both of them are 0, we use the color of the thin lines. This creates the nice effect that we see here, where the larger squares have thick lines around and thinner lines within. Okay, things are looking much nicer now, but we can improve it. Notice that we are still multiplying the final alpha by the alpha of the first LOD. Let's use the correct alpha for each case, where we check whether the alphas are greater than 0. In the case of the thinner lines, we also multiply by the fractional part of the LOD. But this looks weird, so we subtract the fractional part from 1. That's more like it. The final visual touch that I'd like to do is to add some sort of a fall-off effect as we move away from the camera. We can divide the length of the world space position vector by the size of the grid and subtract it from 1. This creates a nice opacity factor, which is closer to 1 near the camera and closer to 0 at the end of the grid. We multiply our current alpha channel by the opacity factor to get the final alpha of the output color. Of course, the length of the world space position becomes greater as we move away from the origin, which destroys the effect. To fix it, we have to subtract the world space position of the camera from the world space position of the grid. So now we divide the relative position from the camera by the size of the grid, so we are not affected by the movement of the camera. And this is it for today. Thank you so much for watching, and I will see you next time.